The periodic table didn't just organize chemistry. It predicted and discovered elements before we even knew they existed. Now, a team of physicists at Emory University has done something remarkably similar for AI. And if they're right, this could fundamentally change how we build machine learning systems. So here's the problem. We're in the multimodal AI era. Systems that combine text, images, audio, video, all at once. Think GPT-4o, Gemini, Claude, the lot. But here's what most people don't realize. Choosing the right algorithm for a multimodal task is largely trial and error. There are hundreds of lost functions out there, and picking up the right one for your specific problem is genuinely hard. That's the gap that this research is trying to close. The paper, published in the Journal of Machine Learning Research, introduces something called the Variational Multivariate Information Bottleneck Framework. A big name with a simple core idea. Most successful AI methods essentially do one thing: compress your data just enough to keep the bits that actually matter for prediction. That's it. The team realized that if you reframe all multimodal AI methods through this lens, they'll fall into a kind of taxonomy. Different methods, different cells in the table, based on what information they retain or discard. Think of it as a control knob. You dial up or down depending on what you need to keep to solve your specific problem. And crucially, this isn't just a neat conceptual trick, it's practical. The framework lets you derive new lost functions more easily, predict whether a given approach will actually work before you train it, estimate how much training data you will need, or identify likely failure pointers in advance. That last one alone could save enormous amounts of compute time and money. The machine learning community has historically been very outcome focused. Does it work? Great, ship it. Why it works sometimes is a bit less important. These researchers come from physics. Their instinct is the opposite. Find the fundamental principle, then derived everything else from it. And that shift in perspective is exactly what produced this result. It's the difference between memorizing the periodic table and understanding atomic theory. One gives you a list, the other one gives you the rules of the game. The practical upshot: less wasted compute, smaller data sets needed, and potentially more trustworthy AI systems, because you actually understand why they are working. Given where we are with AI's energy footprint, that environmental angle is not nothing. The team is already pushing this further. One of the most fascinating directions, applying this to neuroscience. Specifically, can we build a framework that maps the similarities between how machine learning model processes information and how the human brain does? That's not just intellectually interesting. If you can formally connect those two systems, you get insights into both at the same time. This is the kind of work that doesn't make the front page today, but tends to look absolutely pivotal in retrospect. So, a periodic table for AI. The claim is bold. The framework is mathematically grounded. The practical implications are real. Whether it becomes a canonical organizing principle for multimodal AI development or just a genuinely useful tool in the kit, well, we'll see. However, this is the kind of physics meets ML thinking we need more of. I'll link the paper below. Worth a read if you are working in this space. If you found this useful, hit subscribe. I cover this kind of thing regularly. And drop me a comment. Do you think that a unified framework for AI methods is actually achievable, or are we too deep in the empirical chaos for all that? See you in the next one. Thank you.